Hi, my name's Daniel. I'm going to be talking to you today about trustworthy graceful degradation. That is when you've got a big complex service with lots of dependencies, how you can make sure that your application keeps working the way it needs to when some of the less important dependencies aren't working. I work at Stile Education, where we make really incredible, engaging science lessons for high school students that get them thinking critically about the world around them. We also make the cloud platform on which those lessons are delivered into classrooms. Because our product is used live in classrooms, it's really important that it remains available. It's not the kind of product where if it's down for a few hours, everyone grumbles and then moves on with their life. Usually teachers have spent a lot of time preparing their lessons. They come into the classroom, they're standing in front of a whole lot of kids, and they need it to work. That's why we think a lot about how our service degrades gracefully and how it can remain highly available. Come check us out if any of those problems sound interesting. Part of why it's difficult is we've been really successful. A third of students in Australia use our product. That means that during school hours, we have tens of thousands of kids online simultaneously, and across a week we have hundreds of thousands of unique users. Here's basically what Stile looks like. It's a highly available service. We have a TCP load balancer at the front, takes in incoming traffic. We then have an application load balancer that understands HTTP. And then we have a horizontally scalable set of web servers and a database. We use MySQL to store all of our state. Who else works with a service that looks like this? I think the answer is very few of you. If I'm being really honest, Stile looks more like this. We have a lot of extra services beyond the ones that we like to think and talk about. We use Redis as a cache. We even post to Slack when features get released. And the question I want you all to think about is, does your service work when all of those things are down? Or even just when some of them are down, some of the less important ones? Let me tell you a bit of a story about how this can go wrong. So as I said, we use MySQL as our core database. All of our core services use it, and all of the primary workflows in our platform are meant to remain available and functional, even if almost every other data store is down. Mongo is meant to be a secondary database. We experimented with it many years ago. We built some less critical service on it. We decided we didn't like it, and it's thoroughly deprecated now. So I'm going to pick on Mongo for all of my examples in this talk. One day, many years ago, Mongo crashed and Stile went down. We're all like, whoa, that's not supposed to happen. Stile's meant to keep working even though Mongo's not available. So how did this happen? Well, we hadn't actually done the main wrong thing we weren't meant to do here. We hadn't put critical data in Mongo. We hadn't built any of our core services using Mongo. It actually was possible for the application to run as much as it needed to in a class when Mongo wasn't there. What we'd done is made some of our core services depend on some of our less core services, and those services depended on Mongo. And because of the way Mongo happened to crash, a whole lot of processes shut down and needed to reboot, and they couldn't come back up without those secondary services that then couldn't come back up without Mongo. So we were down. Many of you are thinking, well, we're reliability engineers. We have the tools to solve these problems. We're going to run a post-mortem. We're going to establish the root cause. We're going to do 5 whys. We're going to understand all of the different things that went wrong. We're going to fix them all. We're going to tell the engineers, look, you need to remember Mongo is not meant to be a core database. It's not meant to be used in core services. You're not even meant to use secondary services from within core services. And that'll fix it. Until it happens again. Now, a lot of you are probably thinking, well, just telling people not to do it isn't a good enough solution. And you're right, it's not a very reliable solution. But actually, we have a lot of diligent engineers who really thought hard about the problem, and they didn't couple the services together again. In fact, we looked at our API metrics, and it all seemed good. Our core APIs were all returning 200 responses. Some of our secondary APIs weren't. Mongo had crashed, but that was what we expected to happen. So why was everyone telling us Stile was down? This turned out to be the root cause. This is code from our web front end. It's written in JavaScript. So what you've got here is a call to one of our secondary APIs that uses Mongo that was down. And then it returns a promise, and you've got error and success handlers. Now, at first glance, this looks like it's not a problem. We've got an error handler. If that API is not available, we should move on and just not do this particular workflow. What's wrong? The problem isn't even on the screen. Turns out there's a default 30-second timeout on this API call. So every time a class loaded up Stile and went to use it while Mongo was down, they were sitting there staring at a loading screen for 30 seconds. That's enough to make you want to throw your keyboard out the window. To all intents and purposes, Stile was down. So it's not just your error handling and that you have it, it's that timeouts matter too. So The point I'm trying to make here is that it's really easy to mess this up. You can obviously have coupling between services and dependencies that you didn't want. You can also just have broken error handling code. Often your error handling code is less well tested, less well exercised, less well loved than your success handling code. And so it sometimes just won't do what you really need it to in an emergency. And sometimes there's just really rare error states that you don't handle properly because you've never seen them before, or you last saw them many years ago. One of my favorite examples here is we proxy all of our S3 buckets through HA proxy. This is because schools often whitelist very aggressively. They have a firewall listing what websites students are allowed to access. So we put all the resources we need behind our load balancer, including an S3 bucket. By default, HA proxy, it turns out, will cache DNS resolutions indefinitely unless you tell it not to. This meant that when S3 deployed new endpoints for our bucket and then deleted the old ones, we were still sending traffic to those old endpoints which no longer existed, and our users were seeing errors. Now, that's the kind of problem we basically couldn't have detected in development. It's the kind of problem you have to be able to learn from in production. So when you encounter a problem like that, it's really important that you not only learn the lesson and fix the problem, but that you keep it fixed for a really long time, because it's going to be a long time until it happens again, and you may not have the institutional knowledge about how to solve it. I'm just going to run you through really quickly what it looks like to address these sorts of reliability problems. Now, this talk isn't going to be a comprehensive guide to it. There's whole books you can read on it. The Google SRE book has lots. There's plenty of others. But I want to be clear about what sort of systems we're talking about, what it looks like to really fix this. So the first step is really understand all of the different ways your system can fail for each dependency. So all of the application-specific errors for your database. Ideally, you can pop open your database library and just take a look at all the error classes. One I think is often easily overlooked is TCP timeouts. These behave quite differently from other errors. If your database says, you've got the wrong password, that's usually a quick error. You return an error to the client, someone looks at it and fixes it. Often though, there's a really long default TCP timeout configured, often 10, 15, 30 seconds even. And when you're handling that timeout, whatever your request handler is, be it a thread, a process, a coroutine, whatever your web server happens to use, it's not doing anything else. And if you're not careful, you can exhaust all your resources to handle new requests just sitting there waiting for timeouts from your downstream services. So don't forget those. The next step's pretty obvious and intuitive. As soon as you have all the different errors that you need to handle, retry them where it makes sense. Obviously, things like HTTP 503 service unavailable are meant to be retried, but not always. It is application specific and you need to think carefully. S3 uses 503 errors to mean slow down, you're making too many requests. And in that case, if you retry too aggressively, you'll make the problem worse, not better. But the thing that's often overlooked is where you shouldn't retry. And if you're in any doubt about whether you should retry an error, prefer not to retry it. Especially don't retry timeouts for exactly the same reason as I just described with TCP timeouts. If you retry timeouts too aggressively, you'll end up soaking up a lot of your request handling resources just waiting for these downstream services, and it's very easy to exhaust yourself of the ability to handle new requests. More importantly though, if you retry a timeout multiple times, in all likelihood, your clients have gone away in disgust because they've waited so long for their request that they've hit their own timeouts. The nice thing about failing immediately when you hit an error that you don't know what to do with is that it lets your clients retry on their own. Not only can you log great information and make it easy to debug the problem, but your clients can retry if they really need this request to be successful. And when they do retry, hopefully they end up on a whole different process, a whole different container, a whole different server, hopefully even a whole different data center, depending on how your load balancing works. And that means they can work around any errors which are localized to the process which first encountered the problem. If you've got a process that's consistently returning errors, it's really important that you kill that process and restart it. Take it out of rotation as soon as you possibly can. It's more important than you might think, but because of the simple fact that returning an error response is often a lot cheaper than actually doing the work that clients are looking for to generate the results they wanted. This means that if you've got one box out of 100, let's say, that's just returning an error immediately to every request it gets, your SLBs will look at all your boxes and say, this one's actually really free. Every request I send to it, it returns in a couple of milliseconds. I'm going to send more requests to it. So your one box out of 100 might end up handling 50% of your traffic and giving you a huge error rate to your clients, disproportionate to how many boxes are actually unhealthy. you can end up with an unhealthy box or process for all sorts of reasons. You can obviously have hardware problems, a bad network card. You can end up with flags on your database connections which are set improperly due to logic errors in your database driver clients, or logic errors in your own code that are putting the application in a bad state. Ideally, when you restart a process, it becomes healthy again. You get it back to a known good state, you fix whatever's wrong in its memory, but even if it's not, hopefully restarting your process will mean that it can't become healthy initially, it can't pass its initial health checks, and so it will at least stop accepting new traffic. It's really important that by retrying, reconnecting, and restarting, you don't make the problem even worse. It's very easy to accidentally amplify the load that you're putting on your downstream services. Let me tell you a story about how we messed this up. So we were trying to make our Mongo client error handling logic even better. We made the retry and reconnection far too aggressive, and we made it restart processes when it couldn't successfully reconnect. One day, not too long later, our Mongo cluster was overloaded, we had an unusual amount of traffic, and that meant that our application started sending even more connection requests as it failed to answer the first ones. It couldn't answer those either. In fact, that put it under even more stress, so then we sent even more connection requests to it. At some point, we ran out of ports to try and open new TCP connections, and the load average on our Mongo cluster went into the tens of thousands. We had to completely restart the cluster to get it healthy again. It's really important to not restart and retry too aggressively, especially restarting services and processes or bringing new servers online. It can actually cause more than just problems for the downstream service which you're trying to fix. If we restart our process in response to an error connecting to Mongo, our process actually has to connect to all of our downstream services, everything it needs to service traffic, not just to Mongo. And that means that if you're too aggressive in how you restart things, you can actually spread errors across your stack. What I'd recommend is that you have health checks that are tied into your orchestration service, and you teach your orchestration service, if it doesn't do this out of the box, to coordinate restarts across your entire fleet. So have it restart small groups of processes at a time that need to be restarted or brought back to a known good state. I have two different kinds of load checks to power this. One for the orchestrator, which basically says, please restart me. One for the load balancer, which says, can I accept requests? And then you can do a lame duck health check with that load balancer to stop receiving requests just before you restart. And that's advice basically straight out of the SRE book from Google. That was a lot, wasn't it? We talked about a lot of different competing requirements that you need to think through really carefully to be able to handle all the errors properly from each of your downstream dependencies. And I've got bad news for you, because even if you do all of that perfectly, it's not enough. You not only need to do it perfectly the first time, but then you need to not break it. And the errors which exercise this code will be so rare that it's going to be months or even years by the next time that you see these problems and you get to test them out for real. We're at SREcon. A lot of you are thinking, well, chaos engineering is the solution to this. We need to inject faults into production, restart servers, induce network latency, shut down our dependencies, make these problems common enough that you get experience dealing with them and that you know your system works. And chaos engineering is a great tool. I'm going to come back to it in a sec. But there's an even more powerful tool that all of you already have in your stacks. In fact, if you're anything like us a few years ago, then you're severely underutilizing this tool that you already have. And that's CI. You already have a CI system, hopefully, that runs on every code change and checks that all of your code passes a suite of tests before it reaches production. And this is going to sound really basic, but we were underutilizing this a lot. Unit test your service clients, unit test your error handling logic. Here on the screen, I've got a unit test for how our application interacts with our MySQL client. It actually runs a MySQL server in the test. It opens a huge number of connections to the server until the server starts saying, nope, I've got too many connections, go away. And then it checks that our application correctly responds to that error by not trying to open even more connections. Here's another unit test from our code base. It's for our Redis driver. It checks that it handles all sorts of different errors that Redis can return correctly. This kind of test is really important for our Redis driver because Redis is meant to be a cache. So it's quite often the case that if Redis has an error, because it's just a cache, because it's not a primary data store, we can just ignore that error and keep on serving a request. On the other hand, sometimes we use Redis to cache really expensive computations that either take a lot of CPU time or they put a lot of load on downstream services like MySQL, which is really critical for us. We have stampeding herd protection built into our Redis driver, which means that when we've got a really expensive computation like that, we use Redis to make sure that only one of our servers computes that value at the same time. They don't all try to compute it at the same time and potentially overload our downstream services. For that reason, it's really important, and it's quite subtle how we want to handle each kind of error. In some circumstances, you can just pretend that Redis is up, ignore the error, and keep on moving. You can even rerun the computation that was being cached. In other situations, it's critically important that we don't rerun the cached computation because it's so expensive. The other thing that you can do to make sure that this error handling behavior stays working the way you need it to is integration test your system. The way we do this is we have a set of smoke tests that we run on every deploy. These are pretty boring technology. They're written in Selenium. They click around a web browser and test out all of our core workflows, the things that students need to do their work in the classroom, the things that teachers need in the classroom to teach a lesson. We run these on every deploy. We have a blue-green deploy process, so this checks that our new stack has all of the core functionality working the way we expect it to. We also pretty obviously run these in CI to make sure that we haven't broken anything before code gets merged. We actually run multiple copies of these tests in CI, and one of them runs against a cut-down version of our testing stack. It's got none of the dependencies that we believe we shouldn't need in production for these workflows to work. It doesn't have a Mongo server, for example. This means we know that a really basic thing, that our processes can start up when Mongo is not available, but also that the user experience of these core workflows, all the way down to clicking around in our web client, actually works the way we expect. On every code change, we check that that's true. The really good thing about investing in tests for this stuff in CI is that you don't have to discover that you've broken things in production. Instead of having to ship broken code and then roll it back, you instead get to have conversations with your developers about why their tests are failing on CI. Here's an example of a developer who changed some code, wrote a migration that happened to touch our Mongo client in the wrong place. It touched it as part of service startup. Their CI build failed, they asked for help, and you can get into our CI system and find the exact line of code where they introduced a Mongo query in the wrong place that would have blocked a service from starting up without Mongo. The third thing you can do is chaos testing. So chaos testing is super useful. It really tests first how much you actually trust your systems. If you really don't think you need a service, you should be able to shut it down. If that makes you feel uncomfortable, you should really go and invest more in unit testing and integration testing, and even manual testing to make sure that your system's behaving the way you expect. But it's got some limitations. It's really, really powerful when you're expecting to be able to auto-heal from a problem. Kill a process, kill a box. You expect it to restart. You expect your load balancer to handle that error properly and make sure that your clients don't see any errors. If your strategy for handling a service being down, though, is graceful degradation, if you expect your clients to see errors, it's just that they're not important errors in core workflows, or they're only errors in some workflows, it's much more difficult to run chaos tests every day or every week. It's very difficult to run them often enough to get the confidence that you need. For that reason, I'd like to suggest a alternate approach that we use that allows you to get a lot of the same benefits in production. We call this request cursing. The basic idea is that you pick a request as it comes in the front door and you say, you're cursed. For you, we're going to pretend that Mongo's down. It's not going to affect any other requests, it's just going to affect this one request. So this requires a way to add metadata to the handling of a request in your application that then all of your downstream services can inspect. We then go into our Mongo connection library, for example, and teach it before it runs any query on Mongo, it looks for this flag, checks if this request is cursed so that Mongo shouldn't run for it, and then simulates an error that we'd expect to get if Mongo actually wasn't available. And the end result is this. So we wire this up to HTTP request headers so that we can trigger this cursing for requests whenever we want to. You can curl one of our APIs, see it respond successfully. You can curl the same API with a cursing header, so in this case xstyle curse Mongo requests is true, and you get an error response from the API. And this isn't just something you can check by poking at the public API. We can run this, we can then go into our metrics, into our logs, into our tracing systems. All of our observability tools will work to let us see exactly how this request was handled and check that all of our error handling logic for Mongo not being available is working the way we expect. Even better, we can teach our front-end client to set this header on every request for a period of time and browse around. We can check that all of our workflows are working the way we expect, that there aren't timeouts which are frustratingly long, that only the things which shouldn't work are not working. You can also use request cursing to help with your CI tests. So some of you might be running in a testing environment on CI where you've got shared resources. You've only got one MySQL server, all of your tests connect to it. That means you can't do things like I showed you before, where a single test opens a huge number of connections to that database and overloads it. Instead, what you can do is teach your database client to generate the kinds of errors you'd expect when the database is overloaded, in MySQL's case, a too many connections error. You can trigger that behavior with a cursing flag, and then you can have only the tests where you want to exercise that behavior set that flag on your requests. You can use this to test all sorts of weird failure modes that can be difficult to simulate precisely in a testing environment. So an election of Mongo nodes or a failover of MySQL. It can be difficult to coordinate that well for a unit test. It's much easier to simulate it with request cursing. You can even use request cursing to test more abstract services. So now that we're simulating failures for each request, we don't actually need to tie error tests to a single piece of infrastructure. So one way we use this is that we tag all of our routes by what SLO they belong to. We have 3 different SLOs at Stile. We have L1, which is all of our critical services that need to work in the classroom. Then we have L3, which is best effort, and L2, which is right in the middle, which is things that are really important for teachers to prepare their lessons. But if we have to turn them off in a class, that's what we'll choose to do. So we annotate every single API method we have with what SLO it belongs to. This is really useful for us. It lets us do lots of great reporting on our uptime. It lets us do lots of great inspection of our code base to see, how much of our code belongs to different SLO levels. But it's obviously a bit tricky because we want to make sure that these labels are accurate. So one way we test that is by request cursing. We have the ability to turn off all L3 requests, all L2 requests. We run that on our CI system in those smoke tests I mentioned. We disable all L2 and L3 requests. So now we know with really high confidence that all of our core workflows work without any of those requests available. It also means that we know that our L1 routes aren't calling into L2 routes or L3 routes accidentally. If you do implement a system like request cursing, I really recommend just a couple of tips. First, that if you're in a distributed system, you make sure to propagate the cursing flags to all of your downstream services. Make sure that you can see the impacts of a database or a piece of infrastructure not being available everywhere, not just in one service at a time. Second is just set an expiry on the curse. So rather than having a flag saying Mongo is cursed, have a flag saying Mongo is cursed until a time. This means that if you've got downstream services which are synchronizing data between different databases, say for a stats system, they won't stay out of sync forever. That request will eventually be able to succeed and do what it needs to do. Finally, consider restricting access to it. It's not that cursing is a vulnerability in and of itself, but it exposes more surface area from your application, these rarely tested error handling paths, which potentially allows an attacker to exploit things easily that they may not be able to do otherwise. In summary, what I want you to think about today is what are all the dependencies of your system, not just the core dependencies, not just the ones you like to talk about and think about. What are all the ways that they can handle? Have you actually unit tested all of those ways on CI? Do you have integration tests of your whole system without the things that you think you don't need? Have you actually tested the user experience of your system without those things that you think you don't need? Not just the back end, but whether your workflows actually work for your users. And finally, I'd like you to really consider using chaos engineering and a technique like request cursing to check that all of this works in production so that you can check your production config, not just your code. If solving these sorts of tricky reliability challenges while trying to improve critical thinking in the world sounds appealing to you, you should come and check us out, StileEducation.com. We always have a ton of roles open for really talented, brilliant engineers. Come join the team.